Hello guys, welcome to Ramta Solutions and welcome to your lesson on work, energy and power. Today we are looking at work done by a non-conservative force. Okay, so without any waste of time, at the end of this video you must know the definitions of a conservative force and non-conservative forces. You also need to know how to calculate the work done by a conservative force and also the work done by a non-conservative force. I'm hoping that the video will not be long, but if anything, we will then be doing examples. There will be videos with examples, more examples, okay? Videos with more examples, okay? But however, we will try to throw in examples there and there. So without any waste of time, let's define conservative and non-conservative forces. So when we talk conservative forces, in fact, let me say conservative force, we are basically talking about a force for which, or that does zero work, a force that does zero network on any closed path, that does zero network on any closed path, okay, on any closed path. Or you can use a different definition where you will say your conservative force is a force for which, let me write this, it's a force for which work done by or against it only depends only on the starting and ending points of the motion and not the path. Okay, so let me write that down. Force for which work done by or against it depends only on the starting and ending point, or starting and ending point of a motion and not on the path taken. Okay, and not on the path taken. The second definition is the one that I see a lot of you like using. So both definitions are okay, all right? Both definitions are okay. So the second definition, force for which work done by or against it depends only on the starting and ending points of a motion and not on the path taken. Okay? Example of this is gravity, force of gravity, and tension as well. Okay? And tension as well. Okay? However, a very good example is gravity. All right. Now, let's define non-conservative force. A non-conservative force. Now, this one, when it acts, the work done cannot be recovered later as your kinetic energy. Instead, that work done will be converted to other forms of energy. Okay? So the definition of your non-conservative force will be, let's say it's the force for which work done on the object depends on the path taken by the object. Okay? It's a force for which work done by sorry, not by, but work done on the object. Work done on the object depends on the path taken by that object. force for which work done on the object depends on the path taken by that object. On the path taken by that object. Okay, on the path taken by that object. Okay, so something that I also need to mention, coming back to conservative force. With conservative force, mechanical energy is conserved, right? Mechanical energy is conserved. You will remember the law of conservation of mechanical energy in our introduction video to work, energy, and power, right? So when a conservative force is acting on an object, mechanical energy is conserved. But here, when a non-conservative force is acting on the object, mechanical energy is not conserved, right? So remember I mentioned that when a non-conservative force is acting on an object, energy cannot be recovered as your kinetic energy, but it is instead converted to other forms of energy, right? It is converted to other forms of energy, okay? It is converted to other forms of energy, right? Okay, so having said that, we have defined, oh, by the way, examples of non-conservative forces. You have friction and all other forces. Okay, you have friction and all other forces that you can think of. Your applied force, you classify it as your non-conservative force. Okay, all other forces, you classify them as your non-conservative force. Okay, so the only forces so far that we classify as conservative forces are gravity and tension, but more precisely gravity. Okay, perfect. So now let's go look at work done by a conservative force. Okay, work done by a conservative force. I like writing, instead of conservative, I like writing CF. So work done by a conservative force. Remember, I gave you an example of, I said examples of conservative forces are gravity and tension. So let me give you an example. Consider an object. Consider let me say a 2-gram object thrown upwards to height, let me say height what? Height 2 meters above ground, okay? To height 2 meters above ground. Now, calculate the work done for the upward and downward motion. The total work done for the upward and downward motion. Right? Ignore effects of air resistance. Ignore effects of air resistance. So now I want you to consider the situation like this. This is your object. As it goes up, the height here is 2 meters. As it goes up, so this is your object here. I don't know what object it is. It might be a ball or a stone, whatever it is, right? So when it goes up, agree with me that if I were to draw a free body diagram, there are only 2 forces that are acting on this object, which are normal and weight, i.e. gravity, right? So let me not use W, but let me use F sub G, force of gravity, right? These are the only two forces that are acting on the object. So I want you to see something. The force, the work done by force of gravity as this object moves up, you can see to move up, it means your displacement is upwards, but gravity is downwards, right? So let me get this. Work done by a force of gravity as it moves up is F delta X cos theta. And here we're talking force of gravity, so it's mg delta, I shouldn't say delta X, but rather delta Y. Okay, because it's vertical motion, so it's delta Y. Okay, delta Y cos theta. Now, the object is going up, but gravity is going down. So this means our theta is 180 degrees. And now I can substitute. We say we have work done by gravity is 2 times 9.8 times 2 times cos 180 degrees. What is it? It is, let me see, 4 times 9.8, 39.2. So it's negative 39.2 joules, right? So when the object goes up, negative work is done. Now let's look at when the object goes down. When the object goes down, again, I will represent it here. Height is still 2 meters, right? And it's now going down. So again, that free body diagram, it's normal, it's gravity, right? So what we're saying, oh, sorry, I shouldn't be saying normal because it is not resting on any surface. So there's no normal force, it's only gravity. I'm sorry about that. There is no normal force, it's only gravity, right? There is no normal force, it's only gravity. Remember, there can only be a normal force. There can only be a normal force if the object was on a surface, but when it's in the air, there is no normal force. It's only gravity. Okay? Perfect. So there's only gravity here. Now, as you can see, the object is moving downwards, and gravity is also moving downwards. So our angle now is 0 degrees. So the work done to move down is, which is mg delta y cos theta, right? Now, what is it? This is 2 times 9.8 times 2 times cos what? Cos 0 degrees. And this is positive 39.2 joules, right? This is positive 39.2 joules because it's the same thing as this one here. It's only the cosine, the angle that's different, right? So it's positive 39.2 joules, all right? Now, let's find the network. So, the network here, as you can see, is work done to move up plus work done to move down. What is it? To move up, the network was negative 39.2. Yeah, negative 39.2. To move down, it was positive 39.2. Positive 39.2. Now, what is our answer? It is 0 joules. I'm now going to return you to the definition of conservative force. We said it is the force that does 0 net work on any closed path. Can you guys see that? It does 0 net work on any closed path. Okay? It does 0 work on any closed path. So, what we have seen now is that, let me show you. What we have seen now, I'm going to change the color. What we have seen now, or maybe let me continue with it. What we have seen now is that work done when the object goes down is equal to the opposite of work done when the object goes up. Do you guys agree? Yes, it is. Work done when the object goes down is equal to work done when the opposite is equal to the negative of work done when the object is going up. In other words, we can maybe generalize it by saying if you have sub 1 meaning forward motion, sub 2 meaning downward motion or reverse motion, you can say work done for forward motion is equal to the negative of work done for the reverse motion. All right? So having said that, you will recall from this here, we have said, now I'm going to show you now, we have said W net, and in this case, I'm going to say W done by a conservative force. So please allow me to, let me just write conservative, right? W done by a conservative force is equal to work done for upward motion, right? Minus work done or plus work done by downward motion, right? That's what we had said, right? That's what we had said. We have said this will become 0, isn't it? We have said that this will become 0, right? We have said that this will become 0, right? So we now understand that, it'll become 0. But then when you look at it, if you remember well, in our definition, we said, we used mg delta y, which is similar to saying let me use a different color, which is similar to saying mgh. As you can see, this delta y is the height. It's similar to saying mgh, which we said was your potential energy, right? It was your potential energy. Can you guys see that? It was your potential energy, right? Perfect. So now this means now potential energy 1 is equal to negative potential energy down, right? So we can maybe simplify this by saying, what this means for us is that work done by a conservative force is basically, let me use, I don't know why I like using you. So it's potential energy, let's say initial, minus potential energy final, right? Minus potential energy final. Okay, so which we can say, we're not used to it in this way. Let's just take negative as a common factor. We have E P sub F minus E P sub I. And this you have seen before. It is change in potential energy. So work done by a conservative force. Let me do this. Work done by a conservative force is basically equal to the change in negative change in potential energy. It is equal to a negative change in potential energy. It is equal to the negative change in potential energy, right? So now this is where we can leave it for today. And then we will then proceed with, in part 2, we will be looking at work done by a work done by a non-conservative forces. And after doing that, we will basically be done. Trust me, the next video will be a game changer for you. So this is it. If you understand this, you're good to go. All right, guys. So bye-bye.